Thank you very much, Jean-Michel, and thank you very much to the organizers for having organized yet another fantastic Praxis conference. I have been to not all of them. I was not at the first one, but then I think I've been to every one after that one. And I think at that time, one of the main topics of the conference was NMR pulses and shaping for NMR studies. Then other topics came in and conquered the conference or stole the conference. There was something on feedback and engineering, which is still a strong component. Then there was something with gates. Then there was something with quantum measurement theory and sensitivity. So it's actually been moving around and always keeping some of the topics that were there historically. So when thinking about this conference, I thought maybe I'd like to actually give a talk which is not about current research we are doing, but more the bringing together of some of the different cultures that are represented here. So I would like to talk about measurement signals. Of course, we do get measurement signals everywhere, but the measurement signals you get continuously in time. And there's actually different ways to address those signals. Either you integrate your signals and you plot graphs with beautiful mean values, or you can do the kind of trajectories that Juan was showing us yesterday, which are stochastic in nature. When you want to analyze the stochasticity, you can do correlation functions, and that's what people did in quantum optics for decades. But you can also go directly at the trajectories and analyze them in terms of quantum measurement theory. And I like to put those concepts together in this talk, also because these correlations that we find in temporal measurement records are now becoming, well, they have always been interesting, but they are also very interesting today in a number of different contexts that I summarize. So let me start by quoting or setting the stage. So if you take a quantum system, ground states and thermal states, or the steady state of a relaxing quantum system, of course have properties that are sensitive to physical parameters. So you can do sensing of a magnetic field by measuring how much your spins are polarized or precessing in such a field. Dynamics tells more than you find in steady state. And there's a big topic in many-body physics that's called quenched dynamics. You kick the system, or you suddenly change the Hamiltonian to a new value. Your state is no longer in an eigenstate, and it starts evolving. Wow, that's amazing, right? I mean, suddenly you can see some dynamics. Instead of just looking at the eigenstate or the steady state, by changing the Hamiltonian, you get access to a lot of stuff. It's rather trivial when you see it the first time, but it's actually really hot for the past decade or so in many-body physics to exactly target your quantum system that way. Now, yesterday, one was telling us that steady state is boring and dynamics is interesting, and I thought that was a wonderful quote to begin this talk. And so what I will be looking at is dynamics, but I'll actually look at the dynamics you see for a system who is in steady state. And that's actually also what one was talking about yesterday. If you take an open quantum system, then you may have damping and decay that make it relax to a steady state density matrix. This could be a driven two-level system alone or inside a cavity. There's damping of this system, and if you keep driving that system for long enough, just a few lifetimes of the system, then you will find a steady state density matrix. And there will be constant mean values predicted for the amplitude and the intensity of the field leaking out of that cavity. And that's a kind of signal we often see represented in scientific figures. In real experiments, like for example a homodyne detection, you of course get a measurement signal as a function of time. So here I take the light signal or the microwave signal leaking from this cavity, mix it with a strong local oscillator, and then if I split this field 50-50, then these two counters will see almost the same count on average because they see this very strong signal coming down here. But due to interference with your interesting quantum system over here, there's going to be a modulation which effectively measures the amplitude of that field. So that's called homodyne detection. And that amplitude signal, on the other hand, is going to be very noisy. These are counters, and they count huge numbers of photon quanta coming from this source up here. So there will be shot noise in both detector outcomes. So the real signal is actually going to look like this. It's going to be a very noisy signal, and it's going to have an average value who actually represents the mean amplitude of your emitter. Inside this noisy signal, there are correlations. And they are the ones we can characterize simply by taking multiple of the field detected or the signal detected at different times and then averaging and keeping, for example, the time interval constant. So this is one way to analyze such a signal. Another one is to analyze it in terms of quantum trajectories and asking what is the state of this emitter conditioned on the record. as I'm receiving this particular record. And I like to put these two things together in this presentation, and it's actually very well known, and you can read in Howard's book, for example, how these are connected. I'd like to show you a few aspects of this connectedness. The signal is in the noise. That's a thing that was said in quantum optics. When I was a young student, people like Jeff Kimball, the old-timers of quantum optics, they would even sometimes say that there's in fact even no signal modulation at all. Everything is in the noise. And that was, as a student, you think, whoa, quantum physics is fantastic. Sometimes there's not even a mean value, but there's still going to be a correlation. So you don't even see anything changing with time. It's only when you do these two-time correlations or multi-time correlations you can see anything. Actually, I like to moderate that. That's actually not true. When you look at the system, you also see the modulation real time. But the way we analyzed the experiments at that time by density matrices, steady states, there was often no predicted signal going up and down, for example. The signal is in the noise. Still, it's true that there's a lot of information when you look at the noise correlations, and I will comment on that a lot. The work that I'll be talking about here has been done in collaboration with quite a few people. Oh, that was an error in my little device here. But anyway, former students and postdocs. We also had some work together with Kater Merch and his team. And current students are Alexander, who is not here, and Philip, who is here actually at this meeting. The funding for this came from the Velux, which is a Danish company known by all French, because you see these windows everywhere. If you haven't seen, as a tourist to Paris, the Sainte-Chapelle, I strongly recommend it. It's one of the most beautiful places in the world. It's not so far away from Notre Dame. Velux sponsored the cleaning of the windows in that church. It was actually closed for years, but now it is a brilliant, brilliant place to go, actually. So anyway, but they also sponsored our research in Aarhus, actually only by a fraction of the money they gave to Sainte-Chapelle. So photodetection. Well, photodetection, of course, goes back to the 19th century, where it was already observed how photons are detected. And Einstein explained the photoelectric effect using Planck's hypothesis of quantization of light. In fact, you know the story, if your photon energy is less than the work function of the metal, you are not going to release electrons. You're not going to ionize the material. But if you have a shorter wavelength, that is a higher frequency, then you can emit an electron and you can detect the electric signal. The interesting thing about this process that Einstein noted already in 1905 is that the light quantum is actually a wave. It's Maxwell's theory until it is detected, because this absorption process is by a localized classical particle, the electron. So if you have a range of detectors and you send this Maxwell wave, then somewhere you're going to have an electron liberated, and that's, of course, the detection of the photon at that point. But Einstein noted in 1905 that that's actually a problem to understand how the electromagnetic field everywhere in space can suddenly disappear. How can the magnetic and electric field fluctuations at this point know that they should vanish just because the quantum was absorbed there? Einstein was pretty consistent on that point. So in 1905 he didn't like this. In 1927 he didn't like it again when it happened to the electron. So when you have the electron wave function, then again you have a wave which is extending over space, the Schrödinger wave function. But when you see individual electrons being detected here on a photographic film, of course you have again the collapse of the Schrödinger wave function. And he was equally unhappy. Is the electron a wave until it is detected, or what is actually going on in the measurement problem? The observation of wave functions, of course, in quantum mechanics is all over the place. So first electrons, later atoms in atom interferometers, later molecules in these large molecular interferometers. We don't question today that quantum mechanics is describing this wave motion. We are still discussing what it means, but certainly quantum mechanics is right. One thing that is very funny is that as soon as we had quantized matter, people started questioning whether light had to be quantized. So this process, for the photoelectric effect, was for a long time, and is still in many textbooks, written as a proof of the quantization of light. You take an atomic physics textbook, in the first chapter it says, and then the photoelectric effect proves that light is quantized because you have energy conservation. The absorption of the photon quantum exactly is enough to ionize the electron. Then try and go to chapter 13 in the same book, and then they have typically a chapter called photoelectric effect. And the chapter on photoelectric effect calculates this process quantum mechanically, but shining a completely classical monochromatic field on your system. Because you know that if you drive the Schrödinger equation for charged particles with a classical field, then there's a Bohr resonance condition. And that resonance condition has nothing to do with the incoming field being quantized. It just has to do with the frequency of the incoming field. So as soon as you drive quantum matter monochromatically, it doesn't have to be quantum radiation. Actually, classical radiation is good enough. And that started a culture whether light has to be classical or quantum at all. And in fact, many, many optical phenomena can be understood and could be understood as if light was just a classical field. If you want to describe thermal light, maybe you should have it a random classical field. And we had a wonderful talk yesterday about the lamp shift and whether the lamp shift is really a quantum effect. And what was the sort of token of the quantumness was the fluctuation component coming from the vacuum field. But you will notice these could actually have been classical fluctuations. And then you have still not proven that it's a quantum field. They're given by h bar, so the theory is good. But there is a culture that established whether light was actually quantum or not at all. And there's still people who are fighting the fight, saying that we have still not really proven that light is fully quantum. Okay, it's getting more and more difficult. It's a little bit like the discussion of what are they called? These proved tests of quantum mechanics. You know, they are the Asper experiment, but are they really without loopholes or not? So do we have loophole-free tests of the quantum nature of light? And that is still being discussed. So, but one of the big contributions to actually at least convince most of the community that light is a quantum phenomenon came from the measurement of correlation functions. It started with a classical experiment that can't be understood classically. That's the famous Hanbury-Brown and Twiss experiment. This is a stellar interferometer. So there are here two big antennas looking into the sky. And if you imagine that a star is sending out a stochastically fluctuating signal, then when these fluctuation bumps in the signal hit these detectors at slightly different times, then you can tell at which direction in space do you find this object. And if you look a little bit more carefully into the analysis, you can actually even determine the diameter or other properties of this stellar object. So Hanbury-Brown and Twiss, they set up this apparatus and they actually did the experiment. And what they measured was the intensity correlation by these two devices as function of the distance between them. So they're put on train tracks so they can actually vary the distance. And when they varied the distance, they found out that there was a peak in the correlation when they were just on top of each other. And then when you take them further and further away, these intensity correlations, they diminish, simply because the signals become more and more independent if you have larger and larger delays. You can do the same, and they also did the same the year before, actually, with a mercury lamp, where you just take the light, you split it into two, and then you put two counters who, with a delay between them, measure the intensity correlations effectively also at two different times. So if you have a noisy signal where the intensity is fluctuating, there's a simple classical explanation that if this tau is 0, you find the maximum of this function. While if you make tau more and more different from 0, this one is going to fall down and eventually become the product of the mean values. And so that's easy to understand. Hugo Fano, he also offered a tricky quantum explanation. So with the quantum theory of light, how can you actually understand that this thing falls off? And it's inspired, of course, theorists to look more into this. What is actually happening when we measure these noisy signals? And Roy Glauber made his famous theory of photodetection in 1963, which is not only a theory for this experiment, but is actually a theory that describes how any photodetection measurement is to be analyzed in the quantum formalism. And I'll show that thing to you because this is the kind of correlations that led to what we consider the proof of the quantumness of light. So Glauber's photodetection theory says that it's all about the detector clicks. So you have light coming in. In quantum theory, there's an annihilation operator who annihilates the photon, and then you have a charge coming out. So there's some kind of atomic operator, a racing operator, who lifts the electron out of the valence band into the conduction band or into free space, where you can accelerate the electron and detect it. So if you want to know what is the intensity, that should be related to the click rate of this detector. So the probability to get a click, well, you take your state of the field and of the detector electrons, then you apply your Schrödinger equation. So to first order, you have to absorb this photon and create this excitation. So this is the state to lowest order in time. And the probability to have the click is exactly the norm of this last component. So this is the norm of the A gamma dagger acting on this state. And if you take the norm, you just write the adjoint and write it as a scalar product, you see that the intensity is going to be proportional to A dagger A. That's very convenient. That's also the photon number operator. But it's actually, why is the intensity equal to the photon number operator? That's because of this argument. So this is why we get a mean signal who's the mean value of the A dagger A. If you want to have two clicks, one at one time and one at a later time, then you have to evolve your quantum state undergoing the first click at time t, and then you have to release the second electron a little bit later. And again, the intensity correlation function requires you to have both of these clicks, so that should be the norm of this state squared. And you can see I can now write that the same way. You get A dagger, AA, and in this Glauber formalism, it's time ordered, early time, later time, and it's also operator ordered, so it's the A to the right and the A daggers to the left, and that's by this construction. So the real input in Glauber's theory is that take, and that's actually the rule, take the classical quantity you think you want to measure, write it in terms of operators A and A dagger, put all the A daggers to the left, all the A's to the right, and let time increase towards the middle in that expression. So that's Glauber's theory of photodetection. So correlation functions can be calculated now. So you can actually take this classical thing, you can write it as a mean value, and now I should do this operator ordering, and then I can actually, for any source, both the thermal sources, but also a single atom source, calculate this correlation function. Here's a Michelson interferometer where you have a light source. You split the beam in two, so one path may be longer than the other one, and that means that the intensity you get down here will have a cross term between the two passes, and that will actually be a cross term in which you are adding the electric field that took one path and the electric field who took the other one. So you see this quantity squared will have this cross term of the electric field evaluated at two different times from the source. Okay, that also makes very good sense, I mean, because the light you detect down here has two possible delays back to the source. You also know that if you take the Fourier transform of this, or maybe you have seen it, then this is the spectrum of fluorescence. So the way we measure spectrum of fluorescence is by looking at the interference pattern down here as function of this delay, and then you can read out what is the frequency of the field, and you could also read out how well is that frequency defined. The only thing I'm pointing out here in the connection with the topic of this presentation is that, as you see, these are exactly this kind of classical expressions for field at different times, intensities at different times, where Glauber taught us, well, you should really do the A plus A dagger and A plus A dagger, which are the electric field, and then you should normal order them and time order them, and then we actually can tell what you're going to see down here. So which correlation functions correspond to experiments? How do we actually compute these correlation functions if you have a light source? And which of these correlations witness that you have non-classical light? So the last question was a super important question up through the 60s and 70s. I mean, now people were jumping up and down. Now we can finally nail down that there is probably features that are really non-classical. And there's actually papers coming out. There was a FISREV letter earlier this year, which was a new witness that light is actually non-classical, because it was a new elegant test, a new elegant quantity you had to measure to prove now with even less loopholes that this light could not have cheated you and actually been a classical field that hit your detector. So all very exciting. And let me just tell you, because I'm not going to talk so much about the details of this, but the witness is, for example, that these intensity fluctuations go below the mean values at long times. And that's something that is simply not possible for any classical function. So if your detector is hit by a complex number amplitude field, I mean, then the intensity is going to have the value that it has. And if it fluctuates, then tau equal to 0 is going to give you the mean value of I squared. And that's always larger than the mean value squared. Right? But it doesn't have to be like that if you have a single atom who emits photons one at a time. Because as soon as you absorb one, there will not be a second one for you to absorb. And that's, of course, because it's quantum light. And that is witnessed, therefore, by this correlation function. Now let's take a little bit look at what Glauber tells us we should calculate. We should calculate something which is a product of some operator at two different times. Now this is not in your first year quantum mechanics course. What does it mean at all to take an operator at two different times? So there's one place in which you can think about time-dependent operators, and that's the Heisenberg picture of quantum mechanics. So in the Heisenberg picture, operators are time-dependent, so of course I can in principle take such two operators, multiply them, and ask for the mean value. It sounds complicated, and in fact we don't have to go into the Heisenberg picture. There's a recipe also developed all the way back in the late 60s and early 70s, who actually tells us how to calculate these quantities, at least for simple light emitter systems. So if you have a single operator observable you're interested in, then its mean value is given by this expression. You have a density matrix for your system, you have the operator, and if the Schrödinger and Heisenberg picture are the same at a given time, then at that time you just use the density matrix and this fixed operator to give you the mean value. This is what we do all the time when we calculate mean values. Now the density matrix solves a master equation. And the master equation, I don't want to really write it here, but it's a linear equation for the density matrix elements. So it's a lot of terms. They're all coupled to each other in some way. You can formally integrate that just by the exponential of a generator who is doing this expression here. So imagine you write all these elements as in a long string, and then you have a big matrix who gives you the equation evolution, exponentiate that matrix, and you get the time evolved state. I don't know what is that crazy symbol. Oh, that's a 0. Okay. So the state at time t is a period sitting there too, but it's the time evolved state from the initial time. And it's really a linear set of n squared coupled equations. If your Hilbert space has dimension n, you've probably all seen the master equation. If you want to calculate two-time correlations at two different times, you take at time t, the early time, your density matrix and your operator, and you take that matrix you get by multiplying those two together. And then you act with the same generator up for time tau, and then the resulting state you multiply with the matrix B and take the trace. So you see it looks like an expectation value of B, but taken with this new phony state. And it's really not a state. It's not Hermitian. It's not necessarily positive, because rho times A can give you almost anything. But it's a recipe, and it's called the quantum regression theorem. And it really tells you that the way that correlations between different times relax for long times is the same as the single time observables relax for long times, because it's the same relaxation dynamics, it's the same coupling to the bath who causes this decay. So with this tool, we can actually calculate all these Glauber correlation functions that we want. Glauber, he says you should calculate this complicated expression for intensity correlations. Now, the first thing I do is that I say that the electric field emitted is actually proportional to the emitter dipole. So therefore, I replace all the field operators by emitter observables. And then I take the density matrix, because the mean value is the trace of rho times this beast. Then I do a little bit of reordering, because this is at the time t, so I can put it together over here on the left. So you can see I've just taken the last term and put it as the first one. So now I have something at time t and something at time t plus tau. And then I apply this time evolution trick in the quantum regression theorem. So I take this guy, evolve it, and then I multiply with the second term, and this gives me this mean value. And this is how we do it when we calculate this correlation function. And we can do a similar recipe to calculate fluorescence spectra, having only one A dagger and one A term sitting in this expression. This is quantum optics textbook, but it's only a fraction of you who are quantum optics people, so maybe you're not used to do these calculations. Just call me and I'll be happy to do it for you in a microwave setting, if you like. So there's a few anecdotes coming around, because of course we're not just doing the calculations and saying thanks to Glauber we can calculate this. Sometimes we also like to tell, and why do we get the results that we actually get. So some of these anecdotes are a kind of interpretation of what that formula is actually doing for us. And sometimes that can be done in a fairly elegant way. So I just come back to this crazy expression who says that I should take the sigma rho sigma dagger, and then I should evolve it as if it was a density matrix. And then I should take the mean value of sigma dagger sigma at a later time with this as my density matrix. Okay, and I told you that this is generally not a density matrix, but sometimes it is. Because if you take a step-down operator acting, for example, on a two-level system, and then the raising operator on the right-hand side, this is going to give you nothing but the projection into the ground state. This is going to give you a pure ground state as the outcome of that operation. So in this particular case, where sigma takes you from excited to ground, sigma rho sigma dagger is going to be this ground state projection operator. It's as if you are in the ground state. And then there's a number coming out, a prefactor, which is actually, because you have to jump down from the excited state, it's going to be the population of the excited state. So this object here is actually the same as if you reset the atom to the ground state at time t. And then I have to evolve it. And what does that mean? Well, you know what that means. It means you have a system in the ground state and you start solving the master equation. So if there's a laser field driving the system, it will start oscillate up and down and do damped Rabi oscillations, or whatever is happening to your system. So this is going to be the ground state atom evolving. So this is what I've written here. It's actually going to give us, because of this remaining term here, it's going to give me the excited state population time t plus tau, given you were in the ground state at time t. So here's the anecdote. If you want to have 2 clicks from your single atom, you're going to get the first click with a probability, which is the excited state probability, and then you're going to get the second click with a probability, which is what you get from going into the ground state by the first click, and then evolving from that back into the excited state again. That's a wonderful story. That's exactly our picture of what's going on. You get a first click, the atom jumps to the ground state, and then you get a second click later when it has become excited again. And that is actually hiding in this formalism. It also explains the so-called anti-bunching, because this quantity starts being 0 because you are in the ground state. So you have to wait a little bit before this number is actually larger than 0. But there's also another thing that can come from the same thing, and that is if the system is not a 2-level emitter, but a harmonic oscillator emitting, then this A rho A dagger is not going to take you into the ground state. It's going to take you from n to n minus 1, but it's also going to put a prefactor, because you know A acting on n brings out square root of n. So what is going to happen is that a distribution of n states is going to be lowered by 1, but all the higher n probabilities are going to be increased because you have to multiply by this n factor. So you lower the n, but you enhance the Pn values for large n. So in fact, you're going to click a photon, and then you're going to get a state after that who has more photons in it. So when you have a thermal state and you get a click, then the next click is going to come with much higher probability than the first one. And that's because of this interpretation or anecdote version of Glauber's formula. Of course, we can understand it in many other ways, and there are different explanations of this effect. But this way to understand how Glauber's formula is actually leading to this kind of phenomenon that we know from the experiments is interesting to point out. Now, the jumps are, of course, random. So whether this click actually happens at time t or not is not clear. And in this formalism, there is no randomness. You know, I'm not saying that there's a jump. I'm just saying that if I want to know the correlation from t and t plus tau, I have to do this mathematics. There's no actual given predicted times where these jumps occur. There's no structure in the signal. There's only correlations. That's the thing I referred to earlier. But the question is, can you really have correlations in a measured signal if there's not also some structure in that measured signal? And the answer is actually typically no. So in the 1990s, we started modeling this in another way. Using quantum measurement theory, we use quantum trajectories. So this is now so commonplace, and Juan had a wonderful analysis yesterday of the anatomy of these trajectories. So I just say a little bit about them and how they work. And what I really want to show is how they are exactly mapped to the correlation functions we calculate. How the anecdotes become real when you have this trajectory picture. So you have your quantum system. There's some radiation leaving your quantum system. You put a detector out here probing that emitted signal. And the measurement on such a single quantum system, of course, implies measurement back action. So now we are in the theory of quantum measurements. The outcome is random. When you get your random outcome, you have to do something to your quantum state. In standard quantum mechanics, we learn to do projective measurements, and then you have to do the projection on the eigenstate that you measured. This is a little more complicated because I'm not really measuring on the quantum system. I'm measuring on the light who leaves the quantum system. So when I measure a photon, it doesn't mean that the atom is in a definite state. It just means that the atom has emitted that photon. And I have to find out what is that action on the atom at that time. So this measurement has a random outcome. Let's just say that there's a certain set of outcomes, little m. There's a certain probability, that's Born's rule, who tells which one I get with which probability. And if I get a particular outcome, my wave function changes by the action of some operator. This is a projection operator in projective measurement, but can be more general in our case. And then what happens is actually that then the dynamics continues, because this is the initial state of the next time interval. And so you have actually an evolution going on here. And this was promoted by Howard Carmichael and also by Martin Plenio and Gerhard Hegerfeld around 1990, because they wanted to understand how the non-classical fluctuations emerge in detector signals. They understood that the actual noisy detector signals cannot really be understood as a classical noisy process, and it has to involve this extra step that when you do a measurement, there's somebody who remembers what happened in that measurement, and that's the quantum state of the system, who is then triggering what could be the next measurement outcome. There were also other people. There was myself together with Jean Dalibard and Yvan Castin here, who developed exactly the same formalism, but with a more modest ambition, namely to use these wave functions to simulate master equations. So instead of doing the density matrix theory, this is actually a way to simulate what the density matrix is doing for such a system. There was work by Howard Weisman and Gerard Milburn looking at this condition dynamics as a way to control quantum systems, to establish a theory of quantum feedback, which is now really having a high time, because now experimentalists can really go in and implement some of the Howard's ideas from those times. And then, as one said yesterday, there was actually work even before that. So Slava Belavkin did everything and actually had all these aspects in mind before anybody else, of course, and he really did. I mean, it's quite amazing. Barcelli, Nicolas Chizin had a super interesting approach. He wanted to put a nonlinearity in the Schrödinger equation, realizing that if you do that, you can violate special relativity. And then he said, well, how can I avoid violating special relativity? I better put something stochastic too. And then he wrote out an equation, which is the same as the equation that we solve. Also with this other interpretation, it actually means something. And then earlier works, which are more related to this kind of anecdotal interpretation of correlation functions, where both Peter Soller and Erdmer and Cook and Jeff Kimball, who I mentioned, had been talking about why do signal correlations look the way they do. There is probably a physical real jump to the system who triggers the subsequent evolution. So this is, but this was at this anecdotal level. It was not a formalism. It was just an explanation of what we see in these experiments. So here's the quantum trajectory language. You have a quantum wave function. You want to do a measurement who can have a series of different outcomes. Let's say I get outcome little m1. Then my state changes by action of this operator m1. It's part of what is called a POVM. The probability for that outcome is given by this expression sitting here, just the norm of that state. Then after that, you do a next measurement. Time is running and you want to do your next measurement now. You can get an outcome m2. You have to act with operator m2, exactly the same recipe. And of course, what you act on is the state that was delivered to you, namely m1 psi. The joint probability of both events is actually the norm of that state here. So the joint probability of getting first m1 and then m2 is given by this expression. And you can go on and on and on. Measure, measure, measure. You get this whole sequence of actions on your system, and it can be to the limit of being continuous in time. This wave function is making some kind of diffusive process in Hilbert space, and at the same time you're obtaining the measurement record of all these different numbers. This is what we call the conditional quantum state. This is exactly the quantum trajectory, telling you what is the state at this moment in time conditioned on all these outcomes. The data record looks in some funny way, and that's of course constituted exactly by the data you get. And if you want to know about correlations between two different points in that sequence, well, then you can go in and say, what was that data value, and what was that data value at those two different times? So you can see here, there's of course a correlation of those signal values, because the first measurement outcome produces a state, who is the state on which you are subsequently doing the next measurements. So that's why the M1 is going to be correlated with all later measurements. So there's a correlation of signal values, for example, between M1 and M2, because you're measuring on a state that depends on the first outcome. If you want to do the correlation function, we're just not talking about this probability. We're actually talking about what they measure in the lab. So let's say that the number they measure in the lab is actually M1 and M2. This is the signal of this M time-dependent function. So you want to take the mean value of M1 and 2, because I'm showing the correlations between the outcomes. So you measure something, So that quantity you measure is M1 and M2. So you have to ask, on average, what is that correlation function? That's M1 times M2, which are stochastic, weighted with the probability that you get M1 and M2. So this is the correlation function. So this is actually what we should compare with the Glauber theory, if we want to understand how the correlation functions a la Glauber, Heisenberg picture, non-stochastic, are connected to this stochastic theory, who produces the random signal in front of our eyes. And as I told you, the signal correlations are essentially due to the back action and the subsequent evolution of the system. You can even write that the joint probability M1, M2 is the probability to first get M1 and then get M2 conditioned on getting M1 first. So this is just the laws of probability. So you can see that there's a very direct causation between the measurement outcomes you get at different times. So, interlude. Why bother about correlation functions? Well, of course, you were listening to an old man who's looking back on his life, and now it's not because I think I'm going to die tomorrow, but I mean, but there's another reason. There's a current high interest in different time correlation functions in quite many contexts in physics. I mean, if you take a large spin system, for example, you take two spins, then their spins commute at equal time because they belong to two different particles. But if there's interactions along the chain, they don't interact at different times. because this spin is causing the time evolution of its neighbors, who cause the time evolution of its neighbors. So there's a propagation of correlations between such systems. So in some sense, you will have a propagation of the properties of one spin along the whole spin chain, with the speed of propagation, who says that a little bit later, they will not commute at those two different times. So that commutator, or lack of commutation between such two operators, is a measure for how correlations spread in many-body systems. So this is, of course, been appreciated by people who are studying phase dynamics in many-body systems. It's a long time back that Larkin and Ovchinnikov discussed whether momentum observables in the BCS superconductor commute at different times. So at equal times, they are counting how many particles have a certain, or many Cooper pairs have a certain momentum. But if you ask at two different times, they don't commute, of course, because of the interactions in the system. And those interactions can be quantified by that lack of commutativity between these operators. When you do experiments with low-Schmidt echoes where you try to inverse time dynamics, you are sensitive exactly to properties happening at different moments in time. You might even say the Hahn echo pulses, who are refocusing pulses, are trying to undo errors that happen at one moment of time with something that happens in the next moment of time. And some of the final probabilities we measure when we do Hahn echo pulses can be interpreted as two-time correlation function measurements. And I think we'll have talk later today on how you can diagnose with dynamical decoupling the properties of a bath and exactly the temporal properties of a bath. These properties can also witness chaos and many-body phase transition. The word that is fashionable to use now is scrambling. So there's scrambling and propagation of correlations in quantum systems. How does a system relax if it's not an infinite heat bath, but a finite system, and you find this kind of pseudo-thermalization going on? And of the whole story of quenched dynamics too, of course. Quantum thermodynamics, people are interested in how the work done by a system is fluctuating over time. So again, you're interested in maybe taking the integrated work over time, and the variance of such a property involves two-time product of operators. The new black is something called out-of-time order correlations, and it's exactly the things, the kind of correlation functions that Glauber says don't write that correlation functions. So these are the ones where you mix the time order, you mix the normal order, but people are discussing what do these kind of correlation functions signify. So one of the things we're looking at also now. Then another part of the interlude is actually when we do noisy measurements with a purpose. So if you do measurements, for example, counting signals from an atom, you can use that counting signal to estimate how strongly is that atom excited. So at the previous praxis, but not everyone was there, I was talking about estimation doing photon counting. And what you see here is a sequence where we are counting photons emitted by a two-level system, and we are asking what is the Rabi frequency resonantly driving that two-level system. And very quickly, we focus down on a particular value of that Rabi frequency. The mean photon flux from that atom is a function of the Rabi frequency who saturate, because you can only half excite your atom on average. So if the Rabi frequency is higher than 2 or 3, then in fact it's almost a constant level. But here I've actually identified a value of 3 with very high precision. Of course you could say, that's because you have counted 1 million photons, but in fact that figure was made with only 50 photon events. So I've counted 50 photons, and those 50 counting events was enough to tell me that the Rabi frequency was so narrowly defined. And of course, 50 means 50 plus minus square root of 50. So that's a huge error bar, and there's no way from the number 50 to tell that this is the Rabi frequency. But how did we do it? We did it because there are intervals between the clicks, and in those intervals, your wave function is oscillating. So every time you have a click, it's actually because you are predominantly in the excited state. So we are reading out those oscillations. And we are able to distinguish any Rabi frequency equally well because of these rapid oscillations being distinguished by the click intervals in this little story here. There's an associated Fisher information who tells asymptotically, not by simulation, but analytically, that if you integrate with time capital T, then your Fisher information goes as 4T divided by gamma, independent of omega. This is 1 divided by this, the variance in your estimator. So it actually means that your estimator is getting better and better as 1 over square root of time. And how did we calculate that? That's a correlation function calculation. Because this is exactly the measure, clicks, and when does the next click happen. So of course I will not tell you the technique in that, but if you want to know if a given measurement scheme is good or bad analytically or deterministically, then you have to go in and know about the correlations and not the mean values in these click records. And quite general for any measurement scheme, you can try to work out how good is that measurement scheme in terms of sensing. And that will be done by correlation functions. This is the picture I showed you earlier. This is the homodyne detection signal. If I do the same Bayes rule analysis that is trying from the record to estimate what's the Rabi frequency, I can also here fairly quickly achieve a fairly good precision on what is the Rabi frequency driving this system. You don't see anything in this signal. Certainly you don't have the sensitivity to distinguish 2 from 2.5, for example, just from the mean value of the signal, but the way the noise occurs in that signal is actually revealing this to us. And here again, we can actually show that the record here will have a fissure that goes as 4t over gamma, and it's based on the multi-time correlation functions between multiple times in that record. We could even show that no matter what way you measured, you would never be able to do better than 4t over gamma. So that's kind of fantastic that those two detection schemes both reach the optimal for this particular sensing problem. And Madeleine Guter has also pioneered the way to actually extract these kind of fissure information for these kind of records. And Madeleine is also here in the room. So it's funny to see that you can calculate these things, and I just want to point out that if you are in this sensing business, these things are calculated by quantum correlation function calculations. These are deterministic values determined by how signals are correlated over time, because that's where the information is really sitting. Now, I like to come back to the anecdote, and I do the anecdote with a particular experiment that was done in the early 2000s. Very funny experiment where you take an emitter and then you split the signal in two. You put half of the signal or a fraction of the signal to a counter, and you take the other fraction of the signal, mix with a strong local oscillator, and do the homodyne detection. So you say, here you measure intensity, here you measure the field amplitude. So Glauber, he would say, well, the field amplitude you measure at time t plus tau, and the intensity you measure at time t should be governed by this kind of expression, except that since I'm Glauber, I force you to normal order these operators the proper way. And if you have tau later than 0, or you take this t to 0, yeah, tau larger than 0, so this is the later time, then you can see first as you do the a and a dagger at time t, and then in between as you put a plus a dagger, which is the electric field amplitude. If you want to look for the homodyne signal before the click event, then you have to be careful with the ordering. You want all the a daggers first, and you want all the times growing. And if tau is negative, you have to switch those two guys here, right? So therefore you get a slightly more complicated expression. It's still field times intensity, but the rule by Glauber says that this is the quantum expressions we have to calculate. And we can calculate them because the tool is this quantum regression theorem. So of course we can go and calculate what is happening by the quantum regression theorem. And here's the answer. And I show you first the answer only for positive times. So for positive times, it starts out having 0 mean field just after the click, and then you see this oscillating, damped oscillation. And the experiment is done with a single trapped ion in Rainer Blatt's group in Innsbruck. The anecdote works because the click forces you to go into this ground state, just as I told you before, and after that you have to propagate the time evolution and calculate the mean field at later times. So this is exactly what we think we should do. The click takes us to the ground state, and after that, how does the dipole oscillate back towards its steady state? Thank you. So what is going on for negative times? Well, the mathematical formalism works fine, so we can just calculate it, and this is what you see. It's even symmetric in time. Howard Carmichael, who was a theorist on this experiment, he says that it's symmetric because of a detailed balance. That's actually wrong, so I'm happy to show you next that it's wrong. Howard Weissman, who is here, wrote a beautiful paper in 2002 pointing out that these early field measurements, of course, they come before a click measurement. And there's a beautiful theory, well, a kind of controversial theory by Yaki Aharonov about weak values. And the weak value theory is exactly what's the mean value of a thing you measure, conditioned that you later make a strong projective measurement on the same system. Okay, and then he gets anomalous weak values, as they are called. So this structure is what he would call an anomalous weak value, and as Howard proved, well, it's actually just what you get, but it's also a key to understand what's going on. And we had something that was also referred to yesterday in one of the talks, something we call the past quantum state. It's just a systematic way to analyze what do you expect to get at a moment in time if you know all future measurements and all earlier measurements, and we reproduce, of course, also exactly this particular curve. Now, let me because I have only 2 minutes left, let me make just one comment about the trajectory story, because as I told you, it's easy to understand how the click can impose a violent back action on the system, and how the future evolution is therefore going to be conditioned very much on that click event. It's not the same if you do a weak measurement of the homodyne. The signal you measure here is completely dominated by the local oscillator signal. The measurement back action on the quantum system after your measurement of x is almost identity operator. Your density matrix is going to be modified by an operator, I just write it here, but it has a small dt term which depends on the outcome of the measurement, but it's completely dominated by the identity. So you almost do nothing to your state because of this measurement. So it's interesting how this measurement can still even trigger that there should be a click later. And of course, it's not exactly what is happening. What is really happening is that we are not measuring whether you have an x measurement and later a click. We do the mean value of all the x's you get here together with the click you get later. So I'm not supposed to act with a particular x. I'm actually supposed to integrate this over all the x values and multiply with an x, because I'm going for the mean value of x. And when I do that integral with an x in front, the I term gives 0. So I have to pick up these terms here. And therefore, I do get, on average, a strong back action of the weak measurement. But just because the correlation function is actually measuring the value, it's not just looking at that you get some outcome in the measurement. Now, that was clever of me to say that in one sentence, because then I can skip a whole slide. The other view, which is the view by Howard's paper and also by our paper, is that instead of seeing the correlation between the two measurements being conditioning the second one on the first one, you can actually also see if you can condition the first one on the second measurement. And this is really what we are doing. What are you saying, Jean-Michel, about time? I'm enjoying myself, having a good time, but I know that you're all going for lunch, and it's very warm in here. We did a little mathematics. We will skip this thing, because I just want to show you some pictures we did, and then I'll finish after showing this picture. As I told you, it is a little bit magic that curve is symmetric. I don't understand why it's symmetric. I don't know if Howard understands exactly why it's symmetric. We can calculate it analytically, so it is symmetric, but I don't know why. But it's not a rule that it has to be symmetric. So here's a 3-level atom. I'm looking at a count down here, and I'm also looking at the electric signal emitted down here. And in this case, my correlation functions look like this. So you see, it's definitely not the same function on the left and the right. If you have a click, I can anecdotally tell you that I go to the ground state, and then I have some dynamics, which gives these dipole oscillations. On the left, it oscillates twice as fast. Isn't that funny? Okay, so I'll just tell you that story, and then I'll finish, because this is the kind of funny story. So the measurement we do is that I go into the ground state. So when I go into the ground state, then the subsequent evolution takes place from the ground state. Such a 3-level system driven by 2 laser fields has 3 eigenstates. And if they are resonant, then it actually has a dark state, which is a superposition of the 2 extremal ones, and then it has 2 bright states, which are superposition of all 3 states. And those 3 states are all populated in the 1 state, because there's a 1 component in all of these 3 guys. They are separated in energy by the same frequency difference, omega and omega, that you see up here. So that means that being in the 1 state, I'm in a superposition of these states, and since the relative frequency between them is omega, all the observables will oscillate at omega. But the state I have to end up in to get a later click at time here is actually the excited state, because it's the excited state who falls into the ground state. So the state that I have to approach, which is this operator in the Glauber expression, is the excited state 2. And you can see here the state 2 is only present in the 2 extremal states. So I actually have to populate a superposition of those 2 states. They're separated by 2 omega. And that's why this backward evolution runs at 2 omega. So there's no detailed balance in this system. Maybe Carmichael would say it's because it's broken by the 3-level system, and there's maybe even a chiral structure. So he will still be right, because Carmichael is always right. Okay, I'm sorry that I did not plan the time very well. Let me just jump to, and not the next picture, but just show you one little funny thing about the Michelson interferometer that puzzled us for some time and is still puzzling us. So I can calculate the correlation function. I can understand how this gives me the spectrum. Now, I would like to do the trajectory story for the Michelson interferometer too. So I'd like to say, when I have a click down here, what is actually happening to my source? And now there's a funny thing that riddles us a little bit, or is actually challenging us, because the click here, when did the atom emit that photon? And you can see that if I have a click at a certain moment in time, then if there was a short path or a long path back to the emitter, then I actually don't know if this was the time or this was the time that the atom went into the ground state. So this is a situation where we can actually not write down the quantum trajectories of this system, because we don't know when the jumps actually occurred back in the past. But we can use Glauber's correlation function theory, so we can actually calculate what's going on. So with Philip, who is here, we are now working on not only the Michelson, which is the easier one, but also intensity correlations. And it's a challenge, and maybe next praxis will tell you what is the best solution to this particular challenge. And now I have to stop, and I skipped the last slide, but I thank you for your attention.
So thank you very much, Klaus, for this very pedagogic and mind-boggling talk. So I guess we have plenty of questions, because all that is not intuitive. Howard.
So I'm not sure which Howard you were saying couldn't explain why it was symmetric.
Well, you explained everything correctly, but I think it was the other Howard with at least the detailed balance.
Well, so my actual question is about that. Could you, because I never really got a good understanding of that, could you explain what he meant by detailed balance and why it's wrong?
No.
Okay.
No. No, let me give you just one hint. So of course you cannot just say a word like detailed balance. There was, and if you look into the quantum optics literature, there's a lot of these correlation functions who are symmetric. And some of the are symmetric. The intensity, obviously, because click, click, or click, click, you cannot really see the difference. But some of the other ones, because you are in steady state, then properties of Fourier transforms telling you that this has to be a symmetric function, actually, because it's Fourier transform giving the spectrum has to be real. And so there are some symmetries that come in particular in steady state. So I think that because Carmichael is one of the champions of quantum optics, so he knows all these exact cases, he thought that he would just take that argument over in this particular case too.
So you think he would have predicted for your 3-level atom that it would also be symmetric?
Yeah, I think he would have guessed it would be symmetric, but there is actually a later paper by him and his team where they, of course, the experiment was actually done, and it's not symmetric. So in that paper, he doesn't talk about detailed balance anymore.
Okay.
Even great minds can fail.
Yeah, well, it's not a failure. It's a failure of that sort. I would be proud of doing it.
Question over there.
Hi, Klaus. Thanks for the wonderful talk. I've just a question about the quantum regression theorem itself.
Yes.
It's, first of all, a theorem, which means that it's under Markov assumptions,
Yes.
usually.
Yes.
Now, there are people who would argue that you should be using non-Markov models, that there's actually no quantum regression theorem at all, and that if you don't do it in a certain way, you could, for instance, violate thermodynamics.
Absolutely.
Are we actually at a stage where we can experimentally check to see if the quantum regression theorem is a valid assumption in quantum optics?
Yes, I think so. So maybe not in the pure quantum optics, but of course we can make synthetic situations. So what Jan is referring to is if the coupling to the bath cannot be described by perturbation theory and treating the bath as memoryless, which means it should have infinite bandwidth and all correlations going into the bath should immediately go away. If that is not happening, then we don't have the master equation and we don't have the quantum regression theorem either. Sometimes you can get a good approximation to a master equation, but it's strictly forbidden to use that inside the quantum regression theorem. Then we get some of these famous contradictions. So what people have done and are doing is modeling examples, also experiments, where you put an atom in a cavity and then the whole thing radiates. And that cavity is, of course, not infinite bandwidth. So therefore, the atomic dynamics is non-Markovian. In the extreme case, it can emit a photon to the cavity and reabsorb it again before it has leaked out of the cavity. So we can easily have a control knob where we can turn on and off that kind of non-Markovianity just because we make our system part of a larger system, a bit like the spirit of the previous talk, having a larger Hilbert space. And then, of course, there's also the other direction, which is more the praxis community, and that's delay and feedback. So, I mean, there's a lot of work. Howard has done work on that, and Peter Soller and others have developed new methods to deal with that. That's also strictly non-Markovian. And in fact, I would claim that the trajectory I'm talking about in that case is a non-Markovian thing. And even though the atom emits subject to an infinite bandwidth heat bath, so from the point of view of the atom, of course, there's nothing wrong. I'm decaying as always. I'm having a perfect master equation. But if I want to describe that detection record, I'm installing non-Markovianity into the system. And actually, Philip had showed that there are even corrections to the quantum regression theorem popping in when you are messing up the times in this analysis. Mm-hmm. But it is really the frontier to go non-Markovian, absolutely.
Thank you. Another question? Ivan.
I can hear Ivan.
Yeah.
It was for Henri.
So, as another maybe old man, I appreciate the walk down memory lane here. I wonder if you could muse a little bit about what you think the next frontier is for quantum trajectories. Where should we take this in terms of quantum technologies? Or?
I think that as soon as you go to the non-Markovian probing of different quantities, then the sensing theory will have to take that into account. So we just have to understand that. There's the thermodynamics that John referred to. So quantum thermodynamics is hot and super exciting, and it might actually change the foundations of classical thermodynamics, the insights we are gaining there. And there I think that the non-Markovian issues is just super, super important. And then finally, as I also referred to earlier, quantum systems which are run using feedback. We had also a great talk yesterday, late in the afternoon, about applying feedback. What if there's a time delay? I mean, it even seemed in that talk that time delay could be an advantage because you use the memory in the system. And so I think that there's a broad agenda of everything we do in our community, sensing and control of quantum system. I did not even talk about heralding of entangled states here, but of course measurements can also be used to herald interesting dynamics even without the actual feedback. All of that would be subject to change when you have finite bandwidth. We are looking at spin dynamics in microwave cavities, but the cavity itself imposes, of course, a bandwidth issue. So we are really not learning what is the state of that spin in real time, but convoluted in some way. We have to understand this better. So we are not out of the business.
I'm glad to hear that. A last question before lunch? Okay, no, it doesn't seem to be okay. So thank you again, Klaus.